Okay, I want to continue along with something we worked out a while ago, which is our two-dimensional trajectory in the instance of having a linear drag, meaning our drag force is directly proportional to our velocity. This is pretty useful for things that are moving relatively slowly or through a very viscous medium like a marble through honey or something like that. So it's not a great model for something like a baseball or an airplane, which is usually quadratic drag. We'll get to that. For now, let's recall some things that we talked about previously. So first off, I'm going to go ahead and write my drag coefficient this way. I factored out the m, the mass of this object, in my drag force equation. And then what's left is a gamma. So that's my letter gamma. The negative sign means my drag force is always opposite my velocity, and it's proportional to my velocity. We'll still start with the usual initial launch speed v0 and initial launch angle theta. And previously, we used Newton's second law, which is perfectly separable as a differential equation, to solve for both the horizontal and vertical positions of my projectile as a function of time. So this is previous. So our horizontal position as a function of time is my initial launch speed times this letter tau. That's not t, actually. Cosine of my launch angle. Not too surprising that cosine would show up in my x component. And then this decaying exponential piece, 1 minus e to the minus t over tau. What is tau? Tau is defined to be the terminal speed, or terminal velocity, vt, divided by g. What is the terminal velocity, or terminal speed is a better term? That's defined to be g over this drag constant gamma. It's just more convenient sometimes to use the terminal speed and this sort of characteristic time scale when we're writing out our equations, because I don't know about you, but it's really hard to just remember what the units or dimensions of the drag coefficient as defined is, whereas tau stands for a time and vt stands for a speed. So it's a little easier to see dimensionally what's going on. We also found the y component. It's a little more complicated. So there's this bit which has a couple different v's involved. I do see the sine theta show up as you might expect, times tau, not t, and then an exponential term. And then there's this little bit left over, which is minus something times t. This is the part that will gradually get higher and higher, well, I guess more and more negative is a better way to say it, as this goes to infinity. So eventually this thing will approach that aerodynamic wall we talked about. There is some sort of maximal distance away from where the launch position is that you simply cannot get further than at a particular launch angle. This minus something times t tells us that my y position will just sort of grow linearly, not quadratically, but it'll grow linearly with time in the negative direction until eventually it's basically moving at speed vt, terminal speed. Okay, that all is a recall. I don't want to rederive that from scratch, although it's not so hard. Maybe go back and look at that. What I want to do today is take these two parametric equations and eliminate time. I want a trajectory equation. What is y as a function of x, not x and y as functions of time? Okay, so it really is going to be as easy as solving this equation for t, or maybe not entirely for t, but something t adjacent, and plugging it in for the t's here and here in y. So let's go ahead and try to do that. First thing we'll notice is that this 1 minus e to the stuff shows up here as well. And that's easy to solve for. I don't need any natural logs to solve for that bit. So I'll plug that part in first. Notice that this whole thing in parentheses will just be x divided by v0 tau cos theta. Okay, so that first part's not so bad. I'm going to get something linear in x. We even saw that with the standard parabola that doesn't have any drag, that there's always going to be a term that's linear in x to start with. And then there was a quadratic term. Now here, there's not going to be a quadratic term because this t, well, I got to get it out of this t, which is hiding in an exponential. So let's do a little bit of calculation there to see what we're going to add up in this term. So I really do need to solve this bottom piece for t. What does that mean? All right, well, I'm going to subtract 1, flip the sign, and take the natural log. Let's start with that, because that's a lot to do in one step. So I'll have a natural log of 1 minus this junk. And then, okay, I want to actually multiply the tau over, and I'll keep the negative sign. You might say, oh, you could use the negative to like flip the natural log over. Let's not do that because it's attached to a negative anyway here, so it'll look clean once we're done. Knowing this, it's very easy to then get our last term. Okay, so there it is. Like I said, not like super trivial, but we do have y as a function of x. The only places that x shows up are here and inside the natural log. There are no t's left. In fact, one of these taus actually cancels. To slightly simplify it, I guess. Let's erase this bit, and I'm going to just sort of distribute this denominator into these terms to make it look a little more familiar. Okay, so here we have it, y of x. And honestly, that's kind of the end of the problem, but I want to do a little bit more. Because what's the thing we like to do once we have a trajectory equation? I like to calculate the range. I always like doing that. Now, you could get the range from the parametric version. I mean, you could solve for t, the time at which y equals 0, and then plug that in for x. But it's so much cleaner when you can just do it straight off using the trajectory equation, because now I know y equals 0 at the end. So setting y equal to 0, obviously when x equals 0, I get log of 1, which is 0, and I get a 0 here. So yeah, it starts at 0. But I want to know what the other solution is. What is the range? Where does this actually crash? What is this point I'll call r over here? Bit of a problem, because I have a linear term and a logarithmic term. So I've got this transcendental equation that it seems like I have no hope of solving. It's got no quadratic formula for it. How are we going to do this? Well, anytime you have a linear function and either an exponential or a logarithm, you should be thinking of the Lambert function. Now, the Lambert function is most easily written down in terms of exponentials, so I actually do kind of want to undo the natural log here. And just because there's a lot of constants here that I don't want to have to write over and over, let's use some simplifying notation. So I'm going to set the whole thing equal to 0, because that's when it hits the ground, is y equals 0. This whole bit here, which is all a constant, I'll call capital A, and we're multiplying by x. Then I have another constant, which is this vt tau. I'll just write it as b. And then I have the natural log of 1 minus cx, where c is this stuff in the denominator here. Okay, now I want to essentially solve for this x. I am going to get some exponentials, but those are going to be more amenable to the Lambert W-function. All right, so I'll move this over. Exponentiate both sides. And then I'll subtract 1, flip them around, and divide by c. What'll that give me? 1 over c minus 1 over c e to the minus ax over b. Okay, so here is our equation for x in terms of, again, these same sort of constants, but an exponential term. All right, at this point, we have a couple options. One is to recall that there's a general formula for solving any of these equations involving the Lambert function directly. Like we could just write it down. But just to practice how the Lambert function is used, even this is not really the form that I want. Remember, the Lambert function is defined so that if I take the Lambert function of x e to the x, I get x. That's the definition. It's the inverse function, well, two branches of the inverse function of x e to the x. So what I really want to do here is get the x and the exponential together. So you could go use the formula directly right now, but let's practice how we do the algebra of putting things into this form. And to do that, we're really trying to match the exponent to the prefactor. Now I have an x here by itself. I have an x up here that I kind of want to get somehow. Let's go ahead and subtract 1 over c, and then multiply both sides by this e to the positive ax over b. Okay. Getting there. Now let's go ahead and multiply both sides by a over b, because notice that'll give me the right prefactor here-ish. And I'll go ahead and distribute that in. Okay, we're getting there. I've got the ax over b upstairs and downstairs. I just need this extra piece. But that's a constant, so it's totally fine if I multiply this whole thing by e to the minus a over bc. Doing so will put a minus a over bc up into the exponent here, and now my exponent and my prefactor will exactly match. So I'll write that last step in. We've got ax over b minus a over bc e to the ax over b minus a over bc equals negative a over bc e to the minus a over bc. And now it is exactly of the form we want. Exponent and prefactor match. I apply the Lambert function to both sides, and I just get that argument. On the other side, I'm going to get the Lambert function. All right, now it's just a little bit of minor algebra to solve for x itself. Let's see, I'll add that over and then multiply by b over a. And I'll go ahead and factor this out. What will we have? Okay, so there it kind of is. Let's bring this up, and I'm going to go ahead and plug back in these values of a, b, and c. Remember, that's this piece, and 1 over this piece. And we'll see our x, which I'm going to relabel as capital R, it's my range, as a function of these other parameters. Okay, so here's what we wrote down. This is the range. Got our v naught tau cosine theta, but I've introduced a couple new parameters just to keep things a little tidy. First off, this parameter xc is something akin to how far over it's been angled. So it's got the sine theta in it, it's got the y component of the velocity. So we have v naught sine theta over the terminal speed. Notice if this was launched vertically, then sine theta would just give me a 1. And if it's launched horizontally, well, it's not going very far. I would just get a 1. And one could show that this range will end up being 0. It's a little interesting. And then this z is just minus xc e to the minus xc. That's kind of the behavior we've seen in the Lambert function. Linear times exponent with the same prefactor. So this is the range as a function of theta, very implicit, hiding in here, which is in here and here and in here. Often what we do next is we try to maximize the range. What angle gives me the largest range? Now, at first blush, this seems really hard, maybe even impossible. Not entirely so. It's going to be tricky, but not as tricky as you might think. Do not use this. You could try to take the derivative of this, set to 0. You're going to need to know some interesting properties about the derivatives of the Lambert function. It's got all these nasty, like quotient, product, chain rules built in. Ugh. A much better way to do it is actually to go back to the trajectory equation itself and notice that this is equal to 0 when x is equal to r, and take the derivative implicitly with respect to theta. Or, well, there's some explicit dependence, but the r that shows up here and here will get some implicit differentiation. Then you'll be left with an equation to solve. Setting r prime equal to 0 will actually clean that up quite a bit. Let's actually try it out. Okay, so I put our stuff about the range over here using our nice Lambert function. Now I'm going to take the derivative of this expression, the trajectory equation, plugged in x equals r and y equals 0, and we're going to take our theta derivative implicitly. So we're going to need some product rules and chain rules. It won't be so bad. On the left, the first bit, derivative of tangent is secant squared. Derivative of 1 over cosine, which is secant tangent. And then I'll have r. Technically, at this point, I'd use the product rule and do r prime times all of this. But remember, I'm going to set this equal to 0 because I'm trying to maximize r. So I won't write it down. It'd be r prime times the same thing, but that's going to be 0 when we're maximizing. Similarly here, we'll need to use the chain rule. When I take the derivative of the inside, I do have, again, I'm going to call it a product rule because I'm thinking of this as r times secant. And I don't need the second term that's got the r prime in it. I just need the derivative of secant. Okay, so if you didn't follow through that, write it all out using all the product rules, but notice that all the r prime terms are going to 0 because I'm trying to maximize that. And now we can clean this up and try to solve for the r, and try to solve for the theta that maximizes r. Don't forget, we have a formula for r in terms of the Lambert function, but we know what the formula for r is. So let's go solve this for theta. I think I'm going to spare you the gory details. This is just a matter of trying to simplify this, and a lot of it does actually simplify. You can see some tau's canceling already. But I'm going to go ahead and write down a simplified version here without doing all the intermediate steps. Okay, so here's our expression. I didn't really solve for one or the other. But notice that I do have theta and r kind of showing up in a nice way. There's not tons of complicated rational functions of sines and cosines. Now I could take my expression for r that I have here and notice that v naught tau cosine theta will show up on both sides. So this will give me one other nice equation involving xi and z. Okay, so this is what we get after cleaning this up. I went ahead and created one more new variable, u, which is just the initial speed divided by the terminal speed. It's a convenient dimensionless quantity here. We still have this z, which has xi's in it, and xi depends on theta, so it's still kind of messy. At this point, we want to try to get that stuff out of the W function, and you can go back to the definition of the Lambert function to do so. Again, it will take a lot of sort of tedious algebra. I don't want to recreate that whole thing again. So one more time, I'm going to use the magic of editing to get us our final result for sine theta star, we'll call it, the angle that maximizes the range. Okay, here they are. I know I'm skipping a lot of algebra for this, but I think this is better than the tedium. So going and undoing that Lambert function, or kind of applying it to the other side, we're able to find sine theta on its own. I can already kind of see why sine theta is the natural thing that'll show up here. That's the sine theta that shows up in C. The xi shows up in the z, which shows up in the w, and there's more sine thetas here. So we don't need any trig. It's really just solving for sine theta. But here it is. It's this ratio of speeds divided by kind of a complicated expression, the exponential of 1 plus the Lambert function of that ratio squared minus 1 over e, meaning the number e, 2.71828, etc. And then all of that in the denominator minus 1. That is our angle, or the sine of this angle, that maximizes the range. And then if you want to go and take that and plug it back in here to solve for r, at least implicitly, I just quickly did that using that u, we get our actual maximum range. So if I plug in this particular value of sine theta, also I'll need a cosine there, we can get what that maximal range is. Let's look at one special case. What happens if u happens to equal 1? What if we launch this projectile at its terminal speed? That's kind of a special case. In general, this is going to be some pretty complicated function of u, but if we happen to choose an initial launch speed that matches our terminal speed, what does this all collapse down to? Well, it just so turns out that the Lambert function of 0, which is what we would get here, notice that I'd get a 1 squared minus 1 is 0, is 0. The Lambert function the inverse of x e to the x does pass through 0, 0. When x equals 0, x e to the x also equals 0. So that actually simplifies quite a bit. So in our special case over here, if u equals 1, then we end up with kind of the curious relation that sine theta star is 1 over e to the 1 minus 1. And if we just go ahead and plug in those numbers, what do I get? I got about 35.59 degrees. If you're curious, the range in that case does simplify down kind of nicely, involving, again, a trig identity to get your cosine. Excuse me. This E, again, is Euler's constant. And this is approximately, what did I get? Whoops, this is actually not supposed to be squared. 0.514. V naught squared over G. So that's kind of interesting. Notice that in the case of maximal range, when there's no drag, we know that we get V naught squared over G without this extra prefactor. So here, at least in the case where we're launching this at a speed equal to the terminal speed, the range is cut in half, essentially. So not quite as far as you might hope. Okay, to wrap things up now, I want to finish by talking about this vertical aerodynamic wall. And that comes exactly from this natural logarithm. Remember, natural logarithms do have vertical asymptotes where the argument equals 0. So this wall here, and I'm going to go back to where these are just generic x's. This wall is at the location, maybe I'll use green, V naught tau cosine theta. That's the x value for this vertical asymptote coming from the natural logarithm. So sure, its location depends on theta and V naught and also tau, which implicitly depends on the drag coefficient. But we can see that there is no way to get an x value that is larger than this. Even if you let this thing run down to infinity and go as far as it possibly can, there is this wall that limits its location. So that's kind of interesting. All drag problems will always end up having an aerodynamic wall, unavoidable. All right, so quite a bit that we covered here. We got our trajectory equation, replaced that with a y and these with x's. We then found out what that trajectory equation implied about the range, and we even maximized that range. We did have to use the Lambert function a couple times, which is a little tricky, but not impossible. And look at a special case when the initial launch speed matches the terminal speed. And I think that's a good place to stop.